Yes, good morning, everybody. Can you listen to me? Please raise your hand. Yes, good. Thank you. See, we are almost done with DC. We will cruise along to complete the remaining topics here. So the last class, just quick review, just going at least with what we did. See, yesterday we were continuing this maximum power transfer theorem, but this was a special problem where the load side there is a battery also. Okay, so here we cannot reduce the network and directly say load resistance is equal to source resistance. Okay, so but the shortcut is whatever may be the network under Pmax condition, 50% voltage drop across the load. That is the concept I did, and with which we got. Okay, one student was asking, sir, can't we do in exact way? This is the exact way I was telling after the session to the doubt session. See, one student told, how can we do in exact way? For him, I told that you can simplify the network and model the power as a function of E. See, this equation will give you the power equation as a function of E, and then do dP by dE also, you'll get same answer, 7.5 volts you will get. Then another model where characteristics was given but not the network. Then using these characteristics, I modeled the Thevenin's equivalent, and from that we got the answer. Then another classical problem on category 2, VOC by ISC, and again we got the similar answer. Theligen's law of conservation of energy, we started them. Okay, we started Theligen's theorem. Yes, but we are measuring instantaneous power. Okay, yes, this theorem is the only theorem which is working or acceptable for any network, including nonlinear elements or networks. And yes, while applying this theorem, topological arrangement cannot be altered. And while proving this Theligen's, we can also prove for time variance in the excitation. Okay. Then I proved it in a very big problem in IES conventional. The total power delivered is total power absorbed. Then I did some IES bits. Okay. Then I did this gate bit, and also I verified one unique property about Theligen's, that yes, it is valid for any LTI network, but for time variance in excitation. So it is the same network, but defined at two different instances as the sources are varying. Then we came to reciprocity. That was very interesting. Okay, the ratio of response to excitation, okay, remains constant even if you interchange the position of source and load. So I told all the points here. Then see here voltage 68 is giving current 6. Here 68 also will give 6. Then here 123 amperes is giving 48 volts. There 123 is giving 48 volts. Then here use the data given in figure A to find current in figure B. Current is -4. Okay. Then I altered this. And again current is -4. Here you see applied superposition first, and then reciprocity and homogeneity. Here also two sources. So first superposition, then resistivity and homogeneity. Okay, na? So like that, sir, you can do lot of problems. Okay, lot of problems in this area. Okay. Chalo, sir, now let us continue further. Okay, let us continue further, everybody. Yes, now we are going to theorem number 8. Everybody, theorem 8. Okay, that is Milliman's theorem. Milliman's theorem. Okay, Milliman's theorem. Okay, which is also called parallel generator theorem. Parallel generator theorem. Okay, Milliman's theorem or parallel generator theorem. Everybody, this is Milliman's theorem or parallel generator theorem. Now see, in this Milliman's form or parallel generator form, it is applicable only for such networks which are arranged in parallel generator form. So first there is a practical DC generator. Because we are doing DC circuit, what is practical DC source? It consists of small resistance in series. Suppose there is one generator like this. Okay, that is V1 R1. There is another generator. Okay, V2 R2. Like that there are n generators in parallel. Like that there are n generators in parallel. Vn Rn. Okay, between these two terminals. Between two terminals. Okay, let us say X, Y. Okay, suppose there are n generators. Yes, suppose there are n generators in parallel. Okay, I can simplify into single generator. Yes, I can simplify into single generator. X, Y. This is like V millimans, R millimans. So this is applicable only for such networks which are in parallel generator form, sir. So this theorem is not applicable for all networks. Only if they are in parallel generator form. What is parallel generator form? You see here that yes, voltage in series to resistance voltage like that N. Okay, I can now simplify into single network, simple branch consisting of milliamps voltage in series with milliamps resistance. Where now this formulas you have to remember. Milliamps voltage is sigma VI by RI. I taking the value from 1 to n by sigma 1 by Ri. Again, I taking the value from 1 to n. That is also sigma Vi into Gi. Again, I taking the value from 1 to n by sigma Gi. Again, I taking the value from 1 to n. Okay. Also, milliamps resistance is 1 by sigma 1 by Ri. Again, I taking the value from 1 to n. That is 1 by sigma Gi. G is conductance, n branches for n branches. You have to remember, see, this derivation is coming from source transformation technique. Okay, actually, this derivation comes from source transformation technique. Okay, now everybody please understand. Actually, this derivation comes from source transformation technique. Okay, yes, this derivation comes from source transformation technique. Okay, but yes, the derivation is unnecessary, but remember these formulas. So this is very powerful theorem in such cases when the network is in parallel generator form. Now, you know, as electrical engineers, we know all our alternators are parallel, all our loads are parallel. Okay, our alternators are parallel, loads are parallel. Yes or no? Alternators are parallel, loads are, transformers are parallel. So there in such cases we can use. Of course, that is AC circuit analysis. There I will teach again with impedance. So if you learn DC theorem, AC theorem is also oversight, but their impedance concepts will come. Okay, na? Chalo, that is the meaning here. So we can convert any such generator into this form. Okay. Now this is a bit that was asked. Dual of milliamps. What is dual of milliamps? Now listen. Okay, what is dual? See, originally this is the correct meaning of Milliman's theorem. And now don't confuse with Milliman's theorem and Thevenin's theorem, please. Thevenin's theorem can convert any network to voltage source in series with resistance. Yes or no? Thevenin's theorem can convert Thevenin's theorem can convert any network to voltage source in series with resistance. Okay, Thevenin's theorem can convert any network to voltage source in series with resistance. But Milliman's can convert only such a parallel generator form into Milliman's equivalent. Okay, na? Thevenin's can convert any network to voltage source in series with resistance, but Milliman's can convert only such a parallel generator form into this. Okay, na? Remember that. So now in that regard, yes. Now if I go here, now I'm talking about dual of Milliman's. Now here, these are practical voltage sources in parallel. Now what is dual? Practical current sources in series. Now what is practical current source? Current source in parallel with large resistance. Okay, this is the meaning of current source now. Current source I1 in parallel with large resistance R. And such things are in series. Such things are in series. Okay, such things are in series. Okay, such things are in series. Okay, such things are in series between two terminals. Okay, so let us say this is I2R, and let us say this is IM. I can simplify into simple network consisting of current source in parallel with large resistance. This is Milliman's current source IM, and this is dual of Milliman's resistance RM dash L2. Don't confuse. RM dash is different. Originally is RM Milliman's resistance, that is only important, but this is a bit that was also called dual of Milliman's. So here practical current sources in series can be combined into single current source. Here practical voltage sources in parallel can be combined into single voltage source. But this is only practical, sir. This is practical. This is not practical because current source realization is not possible. Current source realizations are not possible everywhere. And in the world, current sources are less, but voltage sources are more. Okay, na? So now this Milliman's current value is, this Milliman's current source value is sigma II into Ri. I taking the value from 1 to n by sigma Ri. Again, I taking the value from 1 to n. Okay, na? Milliman's current source. Okay, sigma I taking the value from 1 to n, so sigma I. Okay, na? And this dual of Milliman's is simply sigma Ri. I taking the value from 1 to n. Okay. Yes, this is sigma Ri. Okay, na? There is a meaning here. Okay, there is a meaning here. Okay, remember these formulas, they all come from source transformation technique. Okay, nothing to worry. Now, very limited problems came, sir, but I am giving you the questions. Chalo, first question. Find current I by using Milliman's theorem. Okay, find current I by using Milliman's theorem. Okay, see here now. This is the question. Okay, everybody watch this question. Find current I by using Milliman's theorem. Volts 1 ohm, 20 volts 2 ohm, 30 volts 3 ohm, 40 volts 4 ohm, 5 ohm, and I need this current I. Okay, find the current I by using Milliman's theorem. Okay, this is my question, everybody. Find the current I by using Milliman's theorem. Okay, I am doing. Everybody watch this solution. Everybody should watch. See, I want current I by using Milliman's theorem. Okay, now because my target is to find current I, which is the target in this 5 ohms, I fix this as my target element. Okay, yes, because my challenge is to find current I, which is a current in 5 ohms. I fix this as my target element, and there I will first bring into Milliman's form. But here voltage source in series, here also voltage source in series. But here current source is in parallel. Nah, first you convert this. Chalo, first if you convert this part alone, okay. Now see, now it becomes what? Voltage source in series here. Here also voltage source in series. But you see, there is a 10 amperes in parallel to 3. Yes, 10 amperes in parallel to 3 become how much? I should be the polarity. Be careful, sir. 10 amperes in parallel to parallel to 3 becomes 30 volts in series to 3. Na? But arrow down, plus down in series to 3. Okay, and this is again 40 volts in series to 4. Okay, na? Yes, this is the first target. Okay, na? X, Y. Okay, so this is 10 volts, 1 ohm, 20 volts, 2 ohm, 30 volts, 3 ohm, 40 volts, 4 ohm. But this arrow down, so polarity down for down positive for 30. Now, if I simplify into first Milliman's voltage, see, I want to now simplify this into Milliman's form. So this can be simplified into simple Milliman's equivalent, where this is Milliman's voltage and Milliman's resistance between X and Y. Between X and Y. Okay, where this is Milliman's voltage and Milliman's resistance between terminals X and Y. Okay, na? So now this Milliman's voltage is, yes, now this Milliman's voltage is sigma Vi by RA. So it is plus 10 by 1, plus 20 by 2, but it is minus 30 by 3 and 40 by 4. Now why minus came for 30? Because see, in my Milliman's equivalent, I took X positive with respect to Y now for Milliman's voltage. So in my Milliman's equivalent, I took X positive with respect to Y. Yes or no? Yes, in my Milliman's equivalent, I took X positive with respect to Y. Now with respect to that polarity, this 10, 20 and 40 are matching. Okay, but 30 is ulta na? This 10, 20 and 40 are matching, 30 is ulta. So that is why minus came. However, resistor is passive bilateral, 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 2. So if you calculate, yes, if you calculate this Milliman's voltage, you will get, okay, yeah, 9.6 volts you will get. 9.6 volts. Then what about Milliman's resistance? This is direct 1 by sigma 1 by RA, 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. Resistance will never have any polarity, it is a bilateral element. Now if you do, this is 12 by 25, 0.48 volts. Now if I simplify the original network into Milliman's equivalent, this resistance is 0.48 ohms. Okay, and this voltage is 9.6 volts between X and Y. So now I am connecting my target. My target is 5 ohms and I need this current now. Yes, this current will be total voltage by total resistance, 5 plus 0.48. Okay, now if you do, yes, 5 plus 0.48, you get 1.75 amperes. This is only in a practice problem. See, he asked us to find current by using Milliman's theorem only. Okay, he asked us to find current using Milliman's theorem only. Okay, he asks us to find current through Milliman's theorem only. Okay, na? So because we need to find current through Milliman's theorem only, yes, Milliman's theorem only. Okay, yes, Milliman's theorem only. So what I did here, yes, I converted this into Milliman's form. Yes, but here voltage source, here current source in parallel become voltage source in series. That is why here what happens, plus is ulta to my reference. So that is why minus 30 came and rest of the things are same. Okay. So now I am giving some gate bits and IES bits. Okay, this is okay. Both are IES bits. Sorry, in gate directly did not come. So in IES objective it was asked. Okay, now this was the question. This can be simplified into option A, option B, option C, and option D. Same terminals. I will give you the options now. XY terminals, XY terminals, VR, 3V3R, V by 3 by 3, VNR. Chalo. Everybody now try to take the correct answer. Try to take the correct answer, everybody. Everybody take the correct answer. I'm giving you 1 minute. Try to take the correct answer. Okay, na? Yes, very good, sir. Very good. I'm good, sir. So many are. See, option is definitely D. Yes, option is D. See, this is the simple bit which was given in IES. This network is simplified into one of the branch. What is the answer? See, because this is in parallel generator form, the fastest way is minimums. What is minimums voltage? Sigma VI by RA. V1 by R1 plus V2 by R2 plus V3 by R3 by 1 by R1 plus 1 by R2 plus 1 by R3. So this is nothing but 3V by R by 3 by R. Yes, 3V by R by 3 by R. There is nothing but V only. Yes or no? What about milliamps resistance? Yes, it is 1 by sigma 1 by R. 1 by R1 plus 1 by R2 plus 1 by R3. So it is R by 3. R by 3. So option is obviously D. Option is obviously D. Yeah. Option is obviously D. Okay. Chalo, very good, sir. We got this. Now I'm giving another IES question. This was also given in Genco. Same bit was given in Genco, copied. Okay. But here no calculators are in IES. So this theorem is powerful in such cases which are in parallel generator form. Two volt, 2 ohm, 4 volt, 4 ohm, 8 volt, 8 ohm, 16 volt, 16 ohm, 32 volts, 32 ohms, 64 ohms. This is A, this is B. Find VAB. That means voltage across 64. That's the meaning. Find VAB. Okay, na? Find VAB. Chalo, 1 minute everyone should try. Find VAB. Everybody please try. Yes, everybody see. Very good, sir. Yes, all the students who are giving answers. Thank you, sir. Thank you very much. See, whether you get correct or not, I don't mind. I told na, sir, we are giving printed notes. Even last day, I will give my WhatsApp number. I will give my personal notes, any material you want, any book you want, solutions you want, everything I will share. But, sir, I told you the logic, na, sir. The secret first to get rank is simple, sir. Do our notes, our material, and previous papers only. If time is there, then we can read textbooks, etc., which is unnecessary. Okay, but already everything simplified from textbook we are giving to you. Chalo, now see, I need VAB. Okay, now because my challenge is to find voltage across 64, I will reduce the rest of the network. Now what I will do, see here, sir. So I will reduce. See, first what I will do, I will remove this 64, then this becomes parallel generator form, and that I will simplify into simple, yes, that I will simplify into simple voltage source in series with resistance. This is the Millman's form. Okay, now between A and B. This is called Millman's voltage and this is called Millman's resistance. But listen, in my Millman's equivalent, I took A positive with respect to B. Yes or no, everybody? In my Millman's equivalent, I took A positive with respect to B. Everyone, please be careful. Yes, in my Millman's equivalent, I took A positive with respect to B. Now, in that regard, these 2 volts, 8 volts, and 32 volts are matching my polarity, but 4 and 16 are not matching. So, this Millman's voltage will be sigma Vi by Ra plus 2 by 2 minus 4 by 4 plus 8 by 8 minus 16 by 16 plus 32 by 32 whole by 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus 1 by R5. See, voltage negative will come, sir, because this 4 is opposite to my reference, so minus came. 16 also is opposite to my reference, where A is positive with respect to B I took, then it is opposite, so minus came. But resistance is passive by little. Resistance will never have that negative. So if you do that, you will get 32 by 31 volts. This is Millman's voltage. And also if you say Millman's resistance, this is direct. 1 by sigma 1 by Ra, 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus 1 by R5. So this is also 32 by 31 ohm. Now once you simplify into Millman's voltage in series with Millman's resistance, okay, this is 32 by 31 volt and this is 32 by 31 ohm. Okay, between A and B. Now I'm connecting my target. So now I'm connecting my target 64 ohms. Now this VAB, voltage division rule, this VAB will be total voltage into same by sum. Same by sum. And that if you simplify, VAB will be 64 by 63 volts. No calculator, NASA, this theorem will help. You may say, sir, why can't I do nodal? You try, sir. If you do nodal, you take LCM, it will be headache. Headache, sir, I'm telling you. But Millman's form is the fastest. Okay, na? Hello, sir. Now we are coming to, yes, substitution theorem. Substitution. Okay, substitution theorem. Very, very interesting, sir. Yes, very interesting. Looks very, looks like very simple, but its applications are tremendous. Okay, substitution theorem. Now look at the statement. In any linear active bilateral network consisting of number of energy sources, okay, with passive elements, okay, understand this. Okay, in any linear active bilateral network consisting of number of energy sources with passive elements. Okay, in any linear active bilateral network consisting of number of energy sources with passive elements. Okay, with passive elements. Okay, any passive element, this is important, any passive element can be substituted in terms of its equivalent voltage or current, and vice versa. Okay, any passive element can be substituted in terms of its equivalent voltage or current and vice versa. Okay, vice versa. For further analysis, for further analysis and reduction in the network, for further analysis and reduction in the network, okay, without disturbing, the rest of the network, without disturbing the rest of the network, okay, provided the power absorbed by the passive element and its equivalent substituted, okay, power absorbed by the passive element and its equivalent substituted, okay, and its equivalent substituted, okay, voltage or current remain same. Okay, it looks very big statement. This statement I am taking from Roy Chaudhary book, sir. See, this big statement I am taking from book called Roy Chaudhary, second edition. Okay, looks very big, but very clear explanation. It's not confusion. Don't worry, sir. Don't worry. When we do problems, you need not remember all these things. But in IAS conventional exams, etc., you better remember because you need to write. Even let it be 6 marks or 8 marks problem, you need to write this. See, in any linear active bilateral network consisting of number of energy sources with passive elements, any passive element can be substituted. Any passive element can be substituted in terms of its equivalent voltage or current and vice versa. For further analysis and reduction in the network without disturbing the rest of the network, provided the power absorbed by the passive element and its equivalent substituted voltage or current remains same. No, okay, don't worry. Now listen, I will explain in a simple way. I will take an example and explain. See, suppose there is a very complex network, okay, and we are observing response in one of the passive element. Of course, in DC circuit analysis, yes, of course, in DC circuit analysis, the passive element which responds is resistance. Okay, chalo. Now for this resistance, okay, I am observing the current and voltage. Okay, now what is this theorem saying? Any passive element can be substituted in terms of its equivalent voltage or current. See, I can substitute this resistance between terminals AB in terms of voltage or in terms of current. In terms of voltage or in terms of current. In terms of voltage or in terms of current. But I'm never saying they are sources. I'm saying these are still sinks only. These are still sinks only because it is a passive element, na, sir. See, here current is entering positive. Here also current is entering positive. So any passive element can be substituted in terms of its equivalent voltage or current and vice versa. Vice versa means similarly a voltage or a current can be substituted in terms of resistance. Any passive element can be substituted in terms of its equivalent voltage or current and vice versa. Okay, any passive element can be substituted in terms of its equivalent voltage or current and vice versa. That means I can substitute a resistance in terms of voltage or in terms of current, but they are sinks only, sir. Don't misunderstand, they are sinks only. See, current entering positive sink. Here also current is entering positive sink. Here also sink. And vice versa. Similarly, remember, any voltage or current which is acting like a sink, can also be substituted in terms of resistance. Any voltage or current which is acting like a sink can also be substituted in terms of resistance. And you can also do this mutual substitution, like here voltage to current and current to voltage, but these are sinks only. Okay, now doing so, what is advantage? You may say, sir, what is the maza in simplifying resistance to this? Or what is the maza in substituting voltage or current which is a sink into resistor? Then reduction become faster. What happens, sir? Here reduction or simplification is faster and simple. That is what is the advantage. But you should never violate law of conservation of energy. That means the power absorbed by this passive element like I square R or V square by R, or even the substituted voltage or current V and I, all should be same. Okay, I square R or V square by R or V into I, all should be same. Okay, now all should be same. There is a meaning. You can substitute resistance in terms of voltage or current and vice versa. Okay, and in doing so, all will be same. Okay, I square r, v square by r, v into I is all same. V into I is all same. Okay, na? So again, listen to the meaning, sir. Now you listen. Any passive element can be substituted in terms of its equivalent voltage or current, okay, or vice versa. Similarly, any voltage or current which is acting like a sink, you can substitute in terms of resistance. But doing so, what is the advantage? Reduction, further analysis and reduction is faster. But it should also be law of conservation of energy. That is power absorbed by this passive element and its substituted element will be same. Okay, sir. First IES objective. See, if if voltage across if voltage across 2 ohm is 20 volts, then 4 ohm resistance between terminals xy can be substituted by voltage of dash value with dash polarity. Okay, if voltage across 2 ohm resistance is 20 volts, then 4 ohm resistance branch between terminals xy can be substituted by a voltage of dash value with dash polarity. Can be substituted by a voltage of dash value with dash polarity. Okay, there is a meaning there. Okay, now I'm giving the network here. This is source voltage E, source side resistance R. This is 2 ohms, 1 ohm, 3 ohm, 1 ohm, 4 ohm. This is terminal X and terminal Y. Now you do this problem, everybody. If voltage across 2 ohm resistance is 20 volts, then the 4 ohm resistance branch between XY can be substituted by a voltage of dash value with a dash polarity. Now, this is not an application, sir. This is only demonstration of substitution theorem, which was given in IES. Okay, this is not the application. We'll do application after one more problem, which is very interesting. But this problem is only demonstration of this theorem. Chalo, everybody write the answer. I'm giving you 1 minute. Read the question carefully and recollect the statement which I gave you and write the answer. Yes, I'm giving the answer. Very good. See here. See. Now first he said voltage across 2 ohms is 20 volts. So this is the voltage across 2 ohms, which is how much? 20 volts. Okay. Voltage across 2 ohms is 20 volts. Okay. Voltage across 2 ohms is how much? 20 volts. Okay. Now why I took this polarity? Because this is the source. Source will drive current and it will divide into two parts. Source will drive current, it will divide into two parts. Okay. So if voltage across 2 ohms is 20 volts, that is the reason I took left side positive, because current enter from left side. Now, if you observe, what is the current then? See, I is V by R. I is V by R. 20 by 2, this is 10 amperes. Now 10 will divide and again it will combine. Now after coming here, if I do current division rule, this current will be total current 10 into opposite 1 by 5. Total current 10. Current division in parallel elements. So this current will be total current 10 into opposite is 1 by 5. So this is 2 amperes. Now when 2 amperes is flowing through 4, this is automatically 8 volts. Now power absorbed by this is how much? Yes, I square R. I square into R, which is clearly 16 watt. Now, sir, now substitution theorem. What is asking? This 4 ohm, yes, this 4 ohm resistance branch can be substituted clearly by a voltage of how much? Yes, 8 volts, 8 volts. Okay, but still the branch current is 2. I'm never changing that. So this voltage source can be substituted. This resistance can be substituted by answer is how much? 8 volts with what is the polarity? X positive with respect to Y. So in fill in the blanks in IES, actually should write this is 8 volts with X positive, okay, with respect to Y. That is the meaning you have to write. So the answer is it is 8 volts with X positive with respect to Y. But here also if you check law of conservation of energy, power absorbed is how much? Voltage into current, that is 16 watts only. Voltage into current 16 watts. So we are not violating any law of conservation of energy. Okay now? Okay, so final answer is 8 volts with X positive with respect to Y. 8 volts with X positive with respect to Y. Okay, now 8 volts with X positive with respect to Y. Okay, now 8 volts with X positive with respect to Y. Okay, now everybody, now this is an IES conventional which was given for 5 marks. Okay, 5 marks, and my question is use substitution theorem. Use substitution theorem, okay, to represent 1 ohm resistance, branch, okay, branch at least in 5 different ways, at least in 5 different ways, okay. Use substitution theorem to represent 1 ohm resistance branch at least in 5 different ways. Okay, use substitution theorem to represent 1 ohm resistance branch at least in 5 different ways. So everybody note down this. I am going to start the solution now immediately. Use substitution theorem to represent, yes, this 1 ohm resistance branch at least in 5 different ways. Okay, 1 ohm resistance branch at least in 5 different ways. At least in 5 different ways. So now if you see everybody, yes, everybody should see this now. Okay, now see, first of all, let us observe what is happening. Now total resistance seen by the source is around 4 parallel to 2 plus 3, 5 ohms. When 10 is seeing 5, it is 2 amperes. 2 amperes will divide the current, then this is automatically 1 ampere. When 1 ampere is going through 1 ohm, it is 1 volt. When 1 ampere is going through 1 volt, 1 ohm, it is 1 volt. Then what is power absorbed? Power absorbed is I square R, which is how much? 1 watt. I square R, which is 1 watt. Okay, na? So now, yes, first I will substitute directly in terms of voltage. Yes, this is also correct. Like between let us say this is terminal AB, I will take. So between AB, this 1 ohm, I can take like 1 volt, 1 amp. So power absorbed is 1 watt. Option B. Again between AB, this is 1 ampere, 1 volt. Power absorbed is again 1 watt. Again 1 watt. So both are sync only, sir. So now I am doing more ways. Okay, now see here. After doing this, now third method. Third method, I will substitute the same 1 ohm as a part of resistance and a part of voltage between AB. This current is still 1 ampere. This is half ohm and this is half volt. What is power absorbed? One is I square R. One is V into I. This is still 1 watt. This is still 1 watt. This is still 1 watt. D. Okay, this is still 1 watt. Now, if you go with the next, see, I can do source transformation. See, I can do voltage source in series can be converted into current source in parallel. Voltage source in series to resistance can be converted into current source in parallel with resistance. Okay, voltage source in series with resistance can be converted into current source in parallel with resistance. Okay, I is V by R, 1 ampere, plus up, arrow up, and this is half ohm. This is half ohm. The system current is still same. Now, if you observe, let us check law of conservation of energy. Now, see, this is 1, this is 1. If you apply KCL 1 plus 1, this is total 2 amperes. When 2 amperes is going through half, this is automatically 1 volt. Now, here, if you see, what is the power absorbed in this case? Now, this is seeing source now. This part has become source now because this is plus and this is minus. Current is leaving positive now, source. Now, for a source, power absorbed is how much? Power absorbed is minus 1 watt. But this is still a sink. What is power absorbed? It is I square R. I square 2 square into R, which is how much? 2 watts. So overall power absorbed. Total power absorbed is again minus 1 plus 2. That is again plus 1 watt only. See, sir. Now another way to represent. See, the original question is represent this 1 ohm at least in 5 different ways. Like first voltage I represented, current I represented, but they are sync only. Here I substituted a 50% in resistance, 50% as voltage. Again it is sync. But I did source transformation for this part. Voltage source in series to current source in parallel. Here plus up, so arrow up. But after substituting like this, if you observe, this became a source. Power absorbed is negative, and this became sync. Power absorbed is positive. But overall power absorbed is positive means overall this branch is again a sink which is absorbing same power. Overall this total system is a sink which is absorbing same power. So we did not violate law of conservation of energy. Then EBIT. Now you can show any combination, sir. Yes, you can show any combination now. Yes, you can show any combination. Yes, definitely. Like I can substitute in terms of something like 0.2 ohm and 0.8 volt. 0.8 volt between AB and this current is 1 ampere. Again, what is power absorbed? Power absorbed is, yes, I square R plus V into, which is again 1 watt. So like that, infinity ways we can show. Okay. So first voltage, current, here 50% voltage and current, here current source in parallel. Again, I take any combination. So like that, infinite ways you can show. Okay, that is the meaning of this question. Like use substitution theorem to represent this 1 ohm resistance branch at least in 5 different ways. Okay, now I'm coming to application question. Chalo, application question. Use substitution theorem. Yes, everybody use substitution theorem to find the value of voltage E. Okay, use substitution theorem to find the value of voltage E for which maximum power is absorbed or maximum power is transferred. Better you write. Maximum power is transferred to the entire load. Use substitution theorem to find the value of voltage E for which maximum power is transferred to the entire load. Use substitution theorem to find the value of voltage E for which maximum power is transferred to the entire load. See, this green box is the entire load. You remember yesterday we did this problem in maximum power transfer theorem? See, yesterday we did this problem in maximum power transfer theorem. Okay, we did this problem in this maximum power transfer. See this problem. Okay, see the same problem. Yesterday we did this problem, but I'm asking you to do by what? Substitution theorem. Yes, use substitution theorem to determine the value of voltage E for which maximum power is transferred to the entire load. Yes or no? Yes, this is very interesting, sir. Very, very interesting. See now. See why this theorem will help us, because the battery is E, which is not allowing us to reduce now. See why we are using this substitution theorem is because this battery is not allowing us to reduce, but we can use substitution theorem. Now, sir, first of all, if this entire load has to absorb power, that to maximum power, then E must be source or sink. First of all, tell me, if this entire load has to absorb power to maximize it, E must be sink. E must be sink. Then what we told in substitution theorem? Any passive element can be substituted in terms of voltage or current, and vice versa. Similarly, any voltage or current which is acting like a sink can also be substituted. See here now. So now I will use substitution that let E is equal to I into R. See, sir, substitution theorem is helping us now because directly I cannot reduce load resistance is equal to source resistance. Why? Because there is a battery E and I need the value E such that it absorbs maximum power. Now, first of all, if it is absorbing maximum power, E must be sink. Now, once it is a sink, now I told substitution theorem that any passive element can be substituted. Yes, any passive element can be substituted. Okay, any passive element can be substituted in terms of voltage or current and vice versa. So this voltage, which is a sink, can also be substituted in terms of resistance. Chalo, now what I will do now, sir? But after doing like this, now see here. Now after substituting like this, now this network becomes like this. What happens now? Same network. Okay, that battery I will remove by substitution theorem. This is still 20 volt, 10 ohm, 20 ohm, 5 ohm, and now this is I into R. I is here, R is here, and this entire thing is the load, Okay, yes, now because it becomes a simple resistance problem for Pmax, we know load resistance is source resistance. Okay, what is the load resistance? 5 plus R in parallel to 20 is equal to source 10. 5 plus R in parallel to 20 equal to 10. So this is 20 into 5 plus R by 25 plus R is equal to 10. Okay, 20 into 5 plus R by 25 plus R equal to 10. Now if you cross multiply, okay, that is nothing but 100 plus 20 R. Yes, and this is nothing but, okay, 250 plus 10 R. So from that I can write 10 R equal to 150. R is 15. Chalo, we got R is 15. Now substitute. Now we got R how much? We got R as 15 ohms. That is under Pmax condition only. Now when R is 15, what is I? Then I is how much? Then for this Pmax, what is I? Now see here. Now total resistance, see now it is reduction. 15 plus 5, 20, 20, 20 parallel 10, 10 plus 10, 20. This is 20 ohms. 20 by 20, this is clearly how much? 1 ampere. 1 ampere will divide, and this is clearly how much here? Half ampere. Half ampere. This is half ampere. Half. Okay, this is half ampere. Then E is I into R for P max. Yes, for P max. Now, if you substitute, I is how much now? I is half. R is how much now? 15. So overall it is how much now? 7.5 volts. 7.5. 7.5. 7.5. Answer. Same answer we got now, sir. Even in maximum power transfer, you check it. See, there is no substitution theorem will simplify in reduction. This problem direct reduction was not possible. Yes, this problem direct reduction was not possible as battery is there. We cannot equate load resistance is source resistance. Then what I did, I substituted this battery in terms of our sink only. Na? So I now simplify into resistance problem. Then load resistance is source resistance for Pmax. Then I got R. Then I got I. Then equal to IR. Equal to IR. Okay, na? Yes, equal to IR. That is the meaning here. That is the real meaning here. Okay, na? Then I am giving IES objective. If the reading of galvanometer is 0, then determine the source current IS. Okay, if the reading of galvanometer is 0, then determine the value of source current IS. The galvanometer. I want this source current value IS. Okay, yes. If the reading of galvanometer is 0, then determine the value of source current IS. If the reading of galvanometer is 0, then determine the value of source current IS. Chalo, 1 minute. If the reading of galvanometer G is 0, then determine the value of source current IS. Okay, see now, yes, some students are giving answers. Very good. See now, if the reading of galvanometer is zero, that means the bridge is balanced now. See, galvanometer is the cross arm or center arm of the bridge now. Yes, galvanometer is in the connection where it is the cross arm or center arm of the bridge. Then when can galvanometer read zero? When the bridge is balanced. So galvanometer reading zero. See, galvanometer, yeah, galvanometer reading zero means bridge is balanced. One thing you know, yes, bridge is balanced. Okay, but our concept of bridge balance is the product of opposite arms are equal. But here one is voltage, which is confusing us. So let us use substitution theorem. See, first of all, bridge is balance means the potential of this point and the potential of this point are equal with respect to any other third point. The potential of this point and potential of this point will be equal with respect to any other third point. Okay. So now in that regard, see if this is with respect, suppose with respect to this bottom node, with respect to this bottom node, if this is 6, this also should be 6 now. With respect to bottom node, if this is 6, this also should be 6. Then only the bridge is balanced and current will not flow here. Okay, now, sure. But directly balanced bridge product of opposite arms is not coming. So let us use substitution theorem. Okay, substitution theorem, where I will substitute this 6 volts as I into R. Chalo, now, sir, now what happens? See, now because of that substitution theorem, now the advantage is, yes, I will now take the same network, first. Okay, yes, I will take the same network, which is 2 kilo ohm, here 4 kilo ohm, here 3 kilo ohm, here 6 volts, and automatically we know because bridge is balanced, this is also 6 volts. Now see, now what I will do, I will substitute this 6 volts in terms of IR. So I will remove this and substitute in terms of IR. Okay, IR. So now it became a resistance problem. But since the bridge is balanced, now it won't work now. Since the bridge is balanced, it won't work. That means what is the condition we know? Product of opposite arms. R into 2K is equal to 4K into 3K. 3 kilo ohms. That is the meaning. See, product of opposite arms. R into 2K is 4K into 3K. So R is 6 kilo ohms. R is how much? Yes, 6 kilo ohms. Okay. Now once R is 6 kilo ohms, okay, and I is automatically how much? I is automatically how much? See, I is V by R, that is 6 volts by 6 kilo. This is 1 milliampere. So we got the answer, sir. So that means this is 1 milliampere and this is 6 kilo ohm. Then only it is 6 volt, na? Then only we substitute as 6 volt. And here already, when 6 volt is across 3 kilo, this is 2 milliampere. When 6 volt is across 3 kilo, 2 milli. So this is 1 milli and this is 2 milli. If you apply Kirchhoff current law here, finally this is 1 plus 2, 3 milliamperes. So IS is 3 milliamperes is the answer. 3 milliamperes is the answer. Okay, na? So IS is finally how much? Yes, it is 3 milliamperes. Okay, 3 milliamperes. That is the meaning. The confusion which was there because of the voltage there in a balanced bridge concept has been removed by substitution theorem. Then it became normal resistance problem. We got the answer. Now I'm going to gate bit here. See, this is a recent gate bit here. If Vs is constant source voltage and IL is constant load current. If Vs is constant source voltage and IL is constant load current, then Pmax occurs in load if value of IL is dash. Read the question and write the answer. Vs is constant source voltage and IL is constant load current, then Pmax occurs in the load if IL is dash. if Vs is constant source voltage and IL is constant load current, then Pmax occurs in the load if value of IL is dash. Okay, if Vs is constant source voltage and IL is constant load current, then Pmax occurs in the load if value of IL is dash. Now look at the answer now. See, if Vs is constant source voltage and IL is constant load current, then Pmax occurs in the load if IL is dash. Again, that means he's representing the load as a constant current drawing element. He's representing the load as a constant current drawing element. Okay, such things we learn in power electronics also, na, sir. Consider the load to be constant ripple free current like that. Yes or no? We listen such things. Now, what are the examples of constant current load like motor with constant torque? In a motor, if torque is constant, current is constant. Similarly, you take an example of heater with constant temperature. Heater at a constant temperature will also draw constant current like that. But this is asking for what value of IL Pmax occurs in it. It is confusing, no, sir? So let us use substitution theorem. Use substitution theorem. What is this theorem now? Yes, what I will do is let IL is VL by RL. Okay, let IL is VL by RL. So what I will do the same thing. I will now write this IL as VL by RL. This is VS, however, this is RS. So this I will write it as VL by RL. Okay, this is nothing but RL and this is nothing but VL. Okay, then I can say first of all for Pmax. First of all for Pmax, first of all I will say RL is RS. Okay, RL is RS. Okay, RL is RS. Okay, and then VL will be VS by 2. VL will be VS by 2. First of all, RL is RS. Okay, RL is RS. Okay, and VL is VS by 2 because under Pmax 50% drop will occur na, and load resistance is so. So then finally, if you substitute back, this IL is VL by RL na, but VL is VS by 2 and RL is RS. So answer is IL is VS by 2 RS. For what value of IL Pmax occurs is VS by 2 RS is the answer. Okay, VS by 2 RS is the answer. Okay, that is the answer. VS by 2 RS. Okay, with these basics, yes, we are all done with these basics and complete DC circuit analysis. That's now we are starting chapter 4. Chapter 4, the biggest one, the biggest in the sense time variance. Okay, this is basics of time variance. Basics of time variance. That is introduction to L and C frequency dependent components. See, until now circuit theory, only ideal DC steady state we did. Until now circuit theory, what we did, sir? Ideal DC steady state analysis only we did. Okay, ideal DC steady state analysis only we did. Okay, now I'm going to, yes, variance, time variance. Okay, chalo. First, in that, properties of inductors. Properties of inductors. Very easy, sir. Listen carefully. Property of inductor. Since V is L di by dt, this is the Ohm's law. First point. For ideal DC excitation, we know di by dt is zero. When di by dt is zero, voltage across inductor is zero. Voltage across inductor is zero. Then what I can write? Yes, inductor acts as short circuit for ideal DC in steady state. That is a complete statement. See, for ideal DC, we know di by dt is zero. It is a constant current. Huh? When di by dt is zero, V is zero. Voltage across inductor zero means inductor acts like short circuit for which waveform? Ideal DC. That too in which state? Steady state. In transient state, no. But inductor acts like short circuit for ideal DC in steady state. Then second point, inductor will never allow sudden change in current through it. Okay, inductor will never allow sudden change in current through it. Inductor will never allow sudden change in current through it. Okay, please understand. Inductor will never allow sudden change in current through it. Now, this also I will explain like this. Why? Because see, from the same Ohm's law, sudden change in zero time means dt tends to zero or dt equal to zero. Sudden change in zero time means dt equal to zero. If dt equal to zero, something by zero becomes infinity now. V becomes infinity, which is violation of law of conservation of energy, sir. How can you generate infinite voltage in zero time? How can you generate infinite voltage in zero time? So please understand this, everybody. See, since V is L di by dt, if dt or delta t is zero, then V becomes infinity. If delta t is zero, V becomes infinity. Okay, that means how can you generate infinite voltage in zero time? How can you generate infinite voltage in zero time, which is violation of law of conservation of energy? That is why we should say this is not possible practically. The inductor will never allow sudden change in current in zero time. That is the meaning. Sudden change in current in zero time. Okay, which is violation of law of conservation of energy. Okay, inductor will never allow sudden change in current in zero time because in zero time, infinite voltage, that is violation. Now practical. Now I am going to practical statement. What is the practical statement? But if we do allow, okay, yeah, change in current. If we do allow change in current through inductor, in short interval of time. Okay, but if we do allow change in current through inductor in short interval of time, that is delta t tends to zero, not equal to zero, then we get impulse voltage across it. Okay, that means same formula, V is L di by dt. If you take, okay, this dt tends to zero, not equal to zero. This dt is small, tends to zero. Then this becomes what voltage? Impulse voltage. That is the meaning. See, ideal DC, no change, it acts like short circuit. Sudden change in zero time is not possible, which is violation of law of conservation of energy because voltage is different as amount of work done. But if you do allow sudden change in current in short interval of time, like I will write like microseconds or milliseconds, like that I will write, not equal to zero. In zero, changing is impossible. Which is violation of law of conservation of energy. But if you change current through inductor in short interval of time, like microseconds or milliseconds, then what voltage will come? Impulse voltage will come. Then what voltage will come? Impulse voltage will come. Okay, then impulse voltage will come. That is the meaning. Then impulse voltage will come. Okay, that is the meaning there. Impulse voltage will come. Okay, then yes, ideal inductors are coiled wires with zero internal resistance. So ideal inductors are coiled wires with zero internal resistance. So power loss is zero. Because no resistance, no power loss. Ideal inductors are coiled wires with zero internal resistance. Okay, zero internal resistance. And that is why ideal inductor means it is only inductor but no resistance. That is the meaning. Then practical inductors. Practical inductors, yes, practical inductors do have some internal winding resistance, some internal winding resistance, internal winding resistance, represented which are represented as coil. Now this is practical inductor, sir. This is practical inductor. L, R, and this is coil. Now this is practical inductor, which is L and R, which is called a coil. Practical inductor do have some internal winding resistance, okay, which are represented as coils. This is the meaning of practical. Then another point, yes, inductors are versatile. Versatile. Versatile means variety. Versatile frequency components. Okay. Inductors are versatile frequency different components, and their analysis can be different. For different types of inputs, different types of input excitation. Okay, input excitations. Okay, inductors are versatile frequency dependent components and their analysis can be different for different types of input excitation. Yes, and mode of operation. I will tell you, sir, and mode of operation. Okay. See, I gave some few points to start this chapter. Properties of inductors. Okay. Yes. Since V is LdI by dt, I told for ideal DC, inductor acts like short. Inductor will never allow sudden change in current in zero time because in zero time infinite voltage is violation of law of conservation of energy. That is why you should say it is not practically possible. So inductor cannot allow sudden change in current. But if you do allow change in current in short interval of time, like in microseconds, but not in zero time, then impulse voltage will come. Ideal inductors are coiled wires with zero resistance, no losses, but practical inductors have, yes, resistance which have losses. Then inductors are versatile frequency different components. Versatile means variety, frequency different components, and their analysis is different for different types of inputs and modes of operation. So now onwards, sir, for DC, inductor short, sinusoidal, lagging, triangular, something else will come, sawtooth, something else will, all we will learn now today. Okay. So that is why I told for different types of inputs and different modes of operation, like DC steady state, AC steady state, transient analysis, okay, low frequency mode, high frequency mode. So all that you have to learn from now onwards. Resistor need not be studied like that, sir. Why? Because resistor is independent to frequency and it is a homogeneous proportional component. So resistor is independent to frequency, homogeneous proportional component. So never confusion came with resistor. In a resistor, sudden voltage will give sudden current, zero voltage will give zero current, ramp voltage will ramp current, parabolic voltage will give parabolic. So resistor is not a thing to worry, but inductors, capacitors are different. Okay, that is why we should now onwards be more careful that we should know what input is given and what mode of operation. Okay, now we will take a break. It is now 8:45. Until 9:15 we will take a break and then I will expand these points. Okay, chalo, we will take a break until 9:15. See, it is 8:45, 9:15, half an hour break. Yes, everybody, see this. We just gave some points on understanding inductor. See, these 7 points will not give everything, sir, but this is the starting points of this chapter. See, so far resistor we studied, and DC steady state also we know. But resistor is a homogeneous proportional component, independent of frequency, so very easy device. But inductors, capacitors are frequency dependent. So different inputs they behave differently, and moreover in different states they behave differently, like DC steady state, AC steady state, etc. But to go there, Nasar, we need to first learn their properties. So first of all, the Ohm's law for inductor is V is LdI by dt. From that Ohm's law only everything I will explain, sir. Please understand. From that Ohm's law only I will explain everything. For ideal DC, inductor short, and inductor will never allow sudden change in current through it in zero time, because allowing current in zero time is violation of law of conservation of energy. Then, then now also, but if you do allow sudden change in current in short interval of time, impulse voltage. Okay, that is practical meaning. Here you can give an example of choke coil. See, here you can write example of choke coil. Choke coil. Choke coil in tube light. Okay, I will write tube light, but that is not a good technical term. Fluorescent lamp. Choke coil in fluorescent lamp. Why choke coil in fluorescent lamp? Because their inductor choke coil will produce high impulse voltage to ignite it. That is what happens. Then ideal inductor, zero resistance. Practical inductor has resistance. Then inductors are versatile frequency dependent components. Okay, versatile frequency dependent components, and their analysis is different for different excitations. So that is why now onwards we should know DC steady state, AC steady state, transient, high frequency, low frequency. Okay, all these transient mode, steady state mode, all this we have to learn and then start the problem. Okay, now that is the meaning of this last point. That is the meaning of this last point. Okay, basics we are learning. Okay, now let us understand even properties of capacitors. Okay, properties of capacitor. Properties of capacitor. Okay, yes, now in determining the properties here also, first of all, since I equal to C dV by dt, which is the Ohm's law. Okay, I equal to C dV by dt is the Ohm's law for capacitor. Okay, now I can write the first point. For ideal DC excitation, dV by dt is 0. So current through capacitor is also 0. So I can say capacitor acts as open circuit for ideal DC in steady state. Okay, capacitor acts as open circuit for ideal DC in steady state. Okay, capacitor acts as open circuit for ideal DC in steady state. The next point, capacitor will never allow sudden change in voltage across it. Sudden change in voltage across it in zero time. That is the meaning. Capacitor will never allow sudden change in voltage across it. That is in zero time. Since I is C dV by dt, if dt equal to 0, then you know, yeah, I will write like this. If dt equal to 0, then I becomes infinity. That is violation of law of conservation of charge. How can you drive infinite current in zero time in any element or wires? Are impossible, na sir? How can you drive infinite current in zero time? Practically everything has ratings. You are violating law of conservation of charge. Okay, so that is why we should say capacitor will not allow sudden change in voltage. So allowing sudden change in voltage in zero time is not possible, which is violation of law of conservation of charge. That is how you have to argue in exam or anyone with, why capacitors will not allow sudden change in voltage? You say sudden change in voltage in zero time will need infinite current, which is not practically possible. Okay. Now, what is a practical statement? But if we do allow sudden change in voltage across capacitor, in short interval of time, like milliseconds or microseconds, etc., then it will drive, yes, then it will drive impulse current. Impulse current it will drive. The practical meaning. So the same thing, suppose I is C dV by dt. Now if this is, yes, if this is in milliseconds or microseconds, then what are these currents? Impulse currents. Impulse currents. What are these currents? Impulse currents. Okay, now these currents are impulse currents. Okay, impulse currents. Okay, that currents are impulse currents. Okay, yes, impulse currents. Okay, that are really going to be what currents are? Impulse currents. Okay, you can show it as impulse currents. Okay, then I can say ideal capacitors. Ideal capacitors are considered to have infinite dielectric resistance. So no leakage currents or dielectric currents, we can say. Okay, no leakage currents or dielectric currents, hence power loss is zero. Hence power loss. Okay, dielectric losses are zero. I will write hence dielectric losses are zero. Hence, okay, power loss is zero. Hence power losses are zero. So what are the meanings, sir? If I take a capacitor, ideal capacitor dielectric resistance is infinite because dielectric is insulator, na sir. Ideal insulator resistance is how much? Infinity. So ideal capacitor dielectric resistance is up to infinity. Ideal capacitor dielectric resistance is up to infinity. That is the meaning there. Okay, ideal capacitors are considered to have infinite dielectric resistance. So no leakage currents, hence power losses are zero. Okay, na? But practical capacitors do have large dielectric resistance, and are represented as practical capacitors do have large dielectric resistance and they are represented as, okay, practical capacitors have large dielectric resistance. They are represented as practical capacitors do have large dielectric resistance and they are represented as. Okay, that is the meaning. And are represented as. That is the meaning there. Okay, this R represents what? Dielectric resistance. That is insulator resistance. It can be mega giga ohms like that. Okay, then capacitors are versatile frequency dependent component. Okay, capacitors are versatile, means variety of frequency dependent component, and their analysis can be different for different types of inputs, for different types of input, and modes of operation. Okay, capacitors are versatile frequency dependent components and their analysis can be different for different types of inputs and modes of operation. Okay, now I will explain this. I will explain all these things. Let us understand what they mean. Okay, let us understand what they really mean. Okay, now everybody. See here. Again, sir, we are just giving some basic points to start the real thing. See, this is not everything on capacitor or inductor. But to start this chapter, yes, we are giving such information. Okay, to start this chapter, we are giving such information. Okay, about capacitors. Okay, what they mean or what does it mean? That is the way we are going with. Okay. So what I told the first point, yes, what I told first point, that for ideal DC, capacitor acts as open circuit because current is zero. Yes, open circuit. But capacitors will not allow sudden change in voltage across it. Capacitors will not allow sudden change in voltage. because in sudden change in voltage in zero time is like infinite current, which is violation of law of conservation of charge. Next, I told if we do allow sudden change in voltage across capacitor, yes, if we do allow sudden change in voltage across capacitor, okay, in short interval of time, okay, impulse currents will come. If we do allow sudden change in voltage across capacitor in short interval of time, then impulse currents will flow. Ideal capacitors are considered to have large dielectric resistance, so no leakage currents, hence power loss is zero. Okay, ideal capacitors are considered to have ideal capacitors infinite, sir. Yes, infinite, because ideal insulator resistance is infinite. Na? Yes, ideal capacitors are considered to have infinite dielectric resistance, so no leakage currents, power loss is zero. But practical capacitors have large dielectric resistance. Okay, and here dielectric losses will occur. Then capacitors are versatile frequency dependent components, and their analysis is different in different applications. See, that is why capacitor in a static wire compensator behavior is different. Capacitor in pulse and digital circuits is different. Capacitor in a fan phase shifting component is different way how to teach. Okay, so capacitor is a memory element. Okay, in memory, static RAM, dynamic RAM, how to teach differently. So capacitors will have different roles in different applications. Just by reading one application, don't conclude anything from now onwards. Okay, especially inductor capacitor from now onwards. Every problem is a very unique application. You have to understand what mode of operation, steady state, transient, low frequency, high frequency, and then also analyze for what input we are doing, and also analyze for what input we are doing. Okay, what input we are doing, that is very very essential. Okay, and we have to analyze for what input we are doing. Okay, is it DC input or AC input or triangular or sawtooth? Okay, that is how we have to learn both. Okay, we have to learn both. Okay, now now with these basics I'm starting the real things, sir. Okay, so first column again, this is basics like what we did in register, but now we are learning for inductor and capacitor. So quickly you have to answer everybody same style, but aggressively we can go now, sir, because already reduction techniques is over. But this is purely inductor problems. I need L total 5 millihenry, 3 millihenry, 6 millihenry, 2 millihenry, 4 millihenry. I want L total. This is gate. Gate 1 mark. What is LXY? Three Henry, 9 Henry, 12 Henry. Okay. 6 Henry, 10 Henry, and this is 5 Henry. So answer these two questions, sir, immediately. Everybody answer these two questions. Here I need L total, there I need LXY. Okay, sir, direct examples, series parallel concept, see here. Now, these are problems without mutual inductance. Now, don't confuse with mutual inductance problems that will come in magnetic circuit chapter with the dot convention. Those problems are very good. We will do later. That after AC steady state, I will teach effect of magnetic link, okay, magnetic flux linkages, Faraday's law. That is different. But right now, see, now these are self inductances only, and there is assume that there is no mutual inductance. Now here 3 milli is in parallel to 6 milli, 18 by 9, 2 milli, 2 milli, 2 milli series 4 milli, 4 milli, 4 milli parallel, 2 milli plus 5 milli. Answer is 7 milli Henry. Okay, na 7 milli Henry. Okay. It is simple series parallel concept, sir. It is simple series parallel concept. Okay, na? It is simple series parallel concept. Now here again you see now. See here if you observe, this is one single node, and this entire thing is also one single node. Okay, this is one single node, and this entire thing is also single node. Okay, but current cannot flow here, na? Yes, current cannot flow here. Please understand. This is one single node, and this is one single node, and current cannot flow here. Okay, because inductor also shorted, it will bypass, so it won't work. Okay, this I can remove. This I can remove. Okay, na? Yes, that is a meaning. Then you see now clearly here 6 plus 3 plus 9, 12, 12, 12 parallel 6, 6, 6 parallel 3, 3 plus 5. Total answer is how much? Total answer is how much? 8 Henry. See now between this node and this node, all are parallel, sir. 3 and 9 parallel, 12, 12, 12 parallel, 6, 6, 6 parallel, 3, 3 plus 5. Yes, if you take 3 plus 5, answer is 8 Henry is the answer. 8 Henry is the answer. Okay, now I'm going to the next question. IES objective. Okay, here also what is LXY? Carefully you do it. LXY. What is LXY? Okay, and then here also what is L total? All are inductance of L Henry. What is L total? Okay, what is L total? Shall I do this? I'm giving only 1 minute now. 1 minute only. Yes, here also everybody see now. See, if you observe, I need inductance between LXY. Now this is like a single node. Okay, this is like a single node. So between this node and this node, these two are parallel. Okay, please understand. This is like a single node between this node. Yes, between this single node and this node, both are parallel. Yes or no, this LL parallel. Between this node and this node, LL parallel becomes L by 2. Okay, so this LL parallel become how much? L by 2. Okay, L by 2. Again, here also between this node and this single node, between this node and this single node, LL parallel again become L by 2. LL parallel again become L by 2. It's also become L by 2. Again, between this node and this node, these two are parallel. Again, LL parallel again become L by 2. Now L by 2, L by 2, 3L by 2. So finally, LXY will be this. L is in parallel to these three are in series, 3L by 2. So our answer is 3 by 5L Henry. 3 by 5L Henry. 3 by 5L Henry is LXY. LXY. Then here also, if you observe, everybody here also, if you observe, I need inductance L total. Now carefully, this is not a short circuit, sir, because there is an inductance here. This is not a short circuit. Okay, now there is an inductance here. But carefully, between this node and this single node, everybody watch this. Yes, between this node and this single node, here all three inductors are parallel. L parallel become how much? L by 3. Yes, L parallel become L by 3. This is L by 3. Again, between this node and this single node, yes, between this node and this single node, okay, between this node and this single node, again L parallel become again L by 3. Again L by 3. This L parallel also become L by 3. L by 3. So on my target terminal, this is one terminal, this is one terminal. I will remove this confusion. I will remove this confusion. Yes, my L total is between these two terminals now. I'm removing these confusions. Okay. Now if you observe, so now if you observe, these three are in series. These three are in series. So this becomes first what? L plus 2L by 3. That is 5L by 3. So finally, this L total will be L in parallel to 5L by 3. So this will be 5 by 8L Henry. 5 by 8L Henry. So the answer will be what? 5 by. These are all simple things, sir. Okay. 5 by. Now this is gate 1 mark. It was given in gate 1 mark. What is LXY? Because first these three are in series, na? I'm getting so many answers. Very good, sir. Okay, now here you see this L plus 2L by 3 is 5L by 3 in parallel to L again. So this is 5 by 8L Henry. Okay, now here I'm asking normal gate bit. What is LXY? Gate 2003 old bit. $10 millihenry, 20 millihenry, 30 millihenry, 40 millihenry, 50 millihenry. What is LXY? Okay, then this is also very important gate 2 marks question. What is L total? 5 Henry, 4 Henry, 2 di by dt. This is I, and this is 3 Henry. And I want L total. 5 Henry, 3 Henry, 2 di by dt, 400, and I want L total. Why Sangeeta raising your hand and Sirisha? Sangeeta, what is the problem? You did raise your hand. Sangeeta, what is the problem? And okay. Any doubt at last only, sir. Please understand. Any doubt, we'll go at last. So now see again, these are both gate bits. 1 mark bit left side, right side bit is 2 marks. What is L total? Wonderful problem. Right side problem is what is L total? Left side problem is what is LXY? Everybody immediately. Are you doing, sir? See, I want you to do. That's why I'm waiting. See, this subject learn while listening over. Nah, sir. Again, there is no time. Nah, there is no time. So that is what. Chalo, now, sir. This is an unbalanced bridge. Everybody look here. This is an unbalanced bridge where the product of opposite arms are not equal. So I will convert definitely one of the delta into star. But this is 10 milli, 20 milli, 30, 40, 50. First scale. See, scale it by magnitude scaling. Scale magnitude. I will write neatly. Scale magnitude, okay, by dividing by 10 millihenry. Then what happens here if you do that? Yes, this left side problem I will do. Then this becomes simply like 1 henry, because you are dividing by 10 milli now. 2 henry, 3 henry, 4 henry, 5 henry, like that it will become, okay now, like you see now, okay. This become like 1 henry, 2 henry, 3 henry, 4 henry, 5 henry, 5 henry, okay now. Yes, I'm not reading units. Now I'll convert one of the delta into star. Now that is what you have to understand. That star delta, delta star in inductor is same like a register formula. So this will be how much? This will be how much? This into this 2 by sum. 2 by 6, 1 by 3, 6 by 6, 1, 3 by 6, 1 by 2. Okay. So I convert one of the delta into star. This becomes something like this. I will convert one of the delta into star. Okay now. Then I can remove this. Then I can remove this. Then I can remove this. Now if I can remove this is 1 by 3 plus 1 by 3 plus 6 in parallel to 4 and a half, 9 by 2. Okay. Now that value again multiply back by 10 milli, because I took magnitude scaling. See here I took magnitude scaling by dividing by 10 milli. Then this became like henries. Then I did delta to star as it is an unbalanced bridge, and again series parallel I will get. But again multiply by 10 millihenry. So if you again multiply by 10 millihenry, yes, if you again multiply by 10 millihenry, and you should get answer. Okay, that will be something like this is 2.904. Overall 29.04 millihenry is the answer. 29.04 million is the answer. 29.04 million is the answer. Okay, na? 29.04. Okay, na? So now right side problem. See, sir, right side problem. It is a problem with dependent source. Na? It is Thevenin's category 1, 2, or 3. So let me see how many will answer. See, we did Thevenin's concepts in register, na, sir? Yes, we did Thevenin's concept in register. Now someone tell me that Thevenin's concept in inductor here. It is category 1, 2, or 3. Anyone? Category 1, 2, or 3? Third category, very good, sir. Because it is a problem with only dependent source, na? Thevenin's category 3. So this is like Thevenin's equivalent category 3. In category 3, what do we do? Apply Ohm's law. Chalo, apply Ohm's law. Apply Ohm's law. So I will do in the next page. So here, if I apply Ohm's law, now watch this, please. But only difference is you cannot give DC signal here. Because if you give DC signal, inductor acts like short. So you have to give a time varying signal and apply Ohm's law. Okay, now. So this is like 5 Henry. This is like 3 Henry. This is plus and minus 2 di by dt. This is I. And this is automatically 4 Henry. Okay. This is 5 Henry, 3 Henry, 2 di by dt, 4 Henry. Okay. Now I will apply Ohm's law. Okay. I will apply Ohm's law. So what I will do, let me inject a time varying voltage V. Let me inject a time varying voltage V. Okay, and I will bring the relation between V and I as this V equal to, okay, L total di by dt. So this L total you can find. This L total you can find. For that I will do mesh analysis. Now listen, sir. This itself is mesh current I, because this input current itself is the source driven current. So this I, and this I will take it as I1. See, sir, here it is like Thevenin's category 3. I cannot give DC. If you give DC, then all di by dt is 0, then dependent voltage source also is 0, short it, then all inductor short. No meaning, na, sir. Now we are applying Ohm's law, but for time variance. Ohm's law for time variance. Ohm's law for time variance we have to apply. Okay, we have to apply Ohm's law for time variance. So here I took a time varying signal V of t, and I'm trying to apply Ohm's law. Now I'm writing the mesh equations. Okay, so now I'm writing the mesh equation. Mesh 1. Mesh 1. Okay, I'm writing the mesh equation. Mesh 1. Yes, now if you look at mesh one, hello, chalo everybody, if you look at mesh one equation, yes, here if you see, yes, minus V of t, okay, plus IR 5 di by dt plus 3 into di by dt minus di1 by dt equal to 0. This is the first equation, ma sir. This is the first equation. So if I simplify further, see, minus V of t plus 5 di by dt plus 3 into di1 by dt minus di by dt minus di1. See here, first mesh current is I, second mesh current is I1. Okay, na? So if you write this V of t is equal to, okay, this is like 8 di by dt, okay, minus 5, minus 3, let me write, minus 3 di1 by dt. This is the first equation. Okay, V of t is equal to 8 di by dt minus 3 di1 by dt. If I go to mesh 2, so if I go to mesh 2, if I go to mesh 2, everybody watch this. This is 3 into I1 minus I1 minus I plus 2 di by dt plus 4 di1 by dt equal to 0 into I1 minus I plus 2 di by dt plus 4 I1 by. Now this becomes how much? Minus 1 plus 2. So di by dt is equal to 7 di1 by dt. This is equation 2. So now apply Ohm's law, solve, put 1 into, so put substitute 2 in 1 and write Ohm's law. So this V of t is equal to, now see this first equation, V of t equal to 8 into di. Now first I will take di by dt as common because that is the total current. Now di by dt if I take common, this will become 8 minus 3, 8 minus 3, but di1 will come. But what is di1 from here? di1 by dt is 1 by 7 of di by dt. di1 by dt is 1 by 7 of di by dt. So 1 by 7 of di by dt. So this V equal to, now 7 8s are 56 minus 3, 53 by 7 into di by dt. This is L total. Wonderful, sir. L total. So the answer. So L total is how much now? 53 by 7 Henry. 53 by 7 Henry. So we applied Ohm's law for Thevenin's. Yes, we applied Ohm's law for Thevenin's category 3 problem. Yes, we apply Ohm's law for Thevenin's category 3 problem. So now I'm giving a unique problem. Yes, I want everyone to answer this carefully. Okay. Now here is question is find steady state currents in each inductor and energy stored in each. Find steady state currents in each inductor and energy stored in each. Find steady state currents in each inductor and energy stored in each. Okay. Find steady state currents in each inductor and energy stored in each. Okay. Now this is the problem I'm giving. Two ohms, 2 millihenry, 1 ohm, 1 millihenry, 6 ohm, 3 ohm, 3 millihenry. Okay, find the steady state currents in each inductor and energy stored in each. So I'm giving you 1 minute, try something, find steady state currents in each inductor and energy stored in each. Determine the steady state currents in each inductor and energy stored in each. Please understand the question. Okay, determine the steady state currents in each inductor and energy stored in each. See everyone, find the steady state currents in each inductor and energy stored in each. Now in that regard, actually this is a transient problem, sir. I know actually when switch closes, transients will occur. And based on the order, like first order or second order, and again in second order, over damped, critically damped, under damped, the responses will come. But he is not asking those, na, sir. He is not asking like find the expression for current for all t greater than 0. Like that is not asking. He is directly asking steady state currents. So though he gave a transient concept problem where switch is closing at t equal to 0, but the solution is for steady state. So steady state means, yes, steady state means t tends to infinity. That means it has settled steady state. Steady state means t tends to infinity. And here what input is given? This is DC. So this is DC steady state. Now in DC steady state, inductor acts like short circuit. So directly if I go in DC steady state, okay, that means the switch has closed and a lot of transients are over, then inductor acts like short. Okay, all inductors act like short. Okay, inductors act like short. Switch has closed. Here also inductors act like short. This is like 60 volt, 2 ohm, 1 ohm, 3 ohm, 6 ohm. Yes. Okay, all inductors act like short circuit. Now I want this current. Okay, this current. Now what is the total resistance in? Now this 1 ohm is completely shorted, sir. This 1 ohm is completely shorted. You can remove this. Short circuit completely in parallel to passive element is redundant. So this 1 ohm is redundant. You can remove it. Okay, this 1 ohm is redundant. You can remove it. Completely shorted. Now 6 in parallel to 3, 2, 2 plus 2, 4. 60 is seeing 4. So this is 15 amperes. This also becomes 15 amperes. Now your current division rule in through two resistors. This current will be total current 15 into opposite 6 by some 9. So 15 into 6, 90 by 9. This is 10 amperes. So the first bit is the steady state currents. The steady state currents in each inductor are 15 amperes, 15 amperes, and 10 amperes. Now what is the energy? Now in steady state I can use half Li square. In steady state we can use energy function as half Li square. Okay, na joules. So now from this energy stored in 2 millihenry is half Li square 15 square, that is 225 millijoules. Energy stored, okay, then energy stored in 1 millihenry is half Li square 15 square, that is 112.5 millijoules. Then energy stored in 3 millihenry, that is half Li square. What is I square? 10 square. Okay, this is 10 square. Okay, this is 150 millijoules. Now all these energies are what form? They are in electromagnetic form. Okay, they are in electromagnetic form held up in the flux around the coil. Okay, electromagnetic form in the flux, in the magnetic flux. Okay, in the magnetic flux around the coil, in the magnetic flux around the coil. Okay, that's the meaning. Where is this energy? See, in resistor, we know resistor converts and dissipates energy in the form of heat. But where is the energy in the inductor means that is in the magnetic field stored around the inductor coil. Okay, there is a magnetic field. Okay, that is the meaning there. So this is directly steady state problem, sir. We got the answer. Okay, na? Now, sir, this is very interesting question. Gate. Find the currents I1, I2. Okay, find the currents I1 and I2. Very interesting. Okay, find the currents I1 and I2. Okay, I want everyone to find the currents I1 and I2. Find currents I1 and I2. Okay, find currents I1 and I2. This is 72 U of t. Okay, step voltage of 72 U of t. This is the meaning. Find currents I1 and I2. Everybody. Find currents I1 and I2. Very interesting. Try to do 1 minute. Everyone sees, sir. Actually, this is a step input of 72 volts and is asking currents. Which currents? Easy asking steady state currents or transient currents or complete solution. See, whenever the question is find currents, that means any question independent to time is considered as steady state. Please understand. Always remember any question if he's asking independent to time or without mentioning time, that is called what question? Steady state question only. So any question independent of time is called steady state question only. Steady state question only. You are understanding? Yeah, any question independent of time is called steady state. Okay, na? That you remember. Any question independent to time is called what, sir? Steady state only. So please understand, it is a steady state question only, sir. Okay, na? Chalo, now in that regard, if it is a steady state question, everybody, yes, if it is a steady state question, okay, then what we can do directly, we can answer. So I know in DC steady state, this 72 volts also 72 U of t. Actually, this is a step voltage. Actually, this is a step voltage where sudden transient occurs at t equal to 0 when suddenly voltage raises from 0 to 72. But because the question is find currents, which currents? Steady state currents. Why they are steady state? Any question independent of time is called steady state. Now in that regard, directly if I go to steady state, yes, this become directly 72 volts DC, 72 volts DC, and for DC inductor short. This inductor is also short. Both are short. Okay, now this is 3 ohms, this is 4 millihenry, and this is clearly 8 millihenry. Okay, now I want these currents I1, I2. Now in steady state, one thing we know, the total resistance in is 3 ohms. So 72 by 3 is how much? 24 amperes. 24 amperes. Okay, 24 amperes and currents. Now both inductors are ideal and there is no resistance. How to divide current? To understand this concept, we need the basics of time variance. We need basics of time variance at t equal to 0 plus. What is the meaning? See, at t equal to 0 plus, you know, the voltage is suddenly raising from, yes, voltage is suddenly raising from what time? See, voltage is suddenly raising from 0 to 72 volts. Yes, voltage is suddenly raising 0 to 72 volts at this t equal to 0 plus. So, at t equal to 0 plus, voltage is suddenly raising. That time, time variance will happen now, but that time variance will happen. That is, this is called transient state. This is called what state? Transient state will give you some secrets. At that transient state, when suddenly changing is happening, okay, the coils are parallel, so induced EMFs must be equal. Induced EMF must be equal since inductors are parallel. Now in steady state, however, inductors act like short circuit and there is no voltage. I know I need steady state answer, but from reaching steady state or before reaching steady state, there is some transient state. Suddenly the change happened, that step voltage came at 0 during the t equal to 0 plus transit period. There is a transient state. That time variance, everything is changing, so induced EMFs will come. Yes, why? Because both inductors are parallel, induced EMFs must be equal. But according to Faraday's law, change in flux linkage should induce EMF. So if yes, flux linkage, so if induced EMFs are equal, flux linkages are also equal. Psi1 equal to Psi2. Okay, which is flux into turn, Weber turns, or you can take Li, Ohm's law. But since again Ohm's law psi is Li, psi is Li, L1 I1 equal to L2 I2. L1 is what? 4 milli into I1. L2 is what? 8 milli into I2. 8 milli into I2. Yes or no? Yes, L1 is 4 milli into I1, L2 is 8 milli into I2. So I1 is 2I2. I1 is 2I2. And also as t tends to infinity in steady state, I1 plus I2 is, however, how much? 24 amperes. That is also second equation. See, sir, how interesting. See, he asked a very simple question, sir. He just asked a simple question that what is I1, what is I2? First of all, any question independent of time is called a steady state. Steady state means settled state. I know in settled state, this step voltage becomes steady DC voltage. Now in steady DC voltage, both inductors are short. So total resistance is only 3, 72 by 3, 24. But how to divide the current, sir? There is no concept here if you don't understand the basics of time variance. Here both inductors are ideal and there is no resistance. How can you divide? Both are like short circuits. To understand that this concept is coming. That is the basics of time variance. That means a transient state t equal to 0 plus when suddenly voltage has changed. This is all valid in the transient state. See, all this explanation is valid when only in transient state, because at that sudden change, induced EMFs are equal, flux linkages are equal, and this is how the currents will divide. And however, in steady state, if you apply KCL, I1 plus I2 should be 24. So solving 1 and 2. Now if you substitute 3I2 equal to 24, I2 equal to 8 amperes, and I1 equal to 16 amperes. That is the final answer. Now you can check, see, also check, now I will write here, also check by current division, current division rule if you do in inductors also, this I1 will be total current into opposite 8 milli by some 12 milli. So total it is 16 amperes. 16 amperes. I2 is also total current into opposite. Okay, 4 milli by some 12 milli. This is how much here? 8 amperes. Yes, same answer you are getting, sir. Same answer you are getting. But if I would have written directly current division rule, everyone would have questioned me, sir. If I would have written directly current division rule, everyone would have questioned me. Sir, how you wrote directly current division? Yes, you will question me, sir, how you wrote directly current division when both are inductors with ideal. Now, this secret comes from this explanation. So that is why this topic in the left side is very important. In the transient state or transit state, when everything is changing, voltage, current, flux, this argument is valid. That, yes, induced EMFs are equal, both coils are parallel. Okay, there is an impulse voltage. You can say it is like an impulse voltage. Okay, then flux linkages must be equal, and from this is how the currents will divide. I know, however, in steady state, inductors act like short circuit, then voltage across them is zero, please. Okay, in steady state, inductors act like short circuit, but this is valid in which state? Transient state. That is why from here onwards, sir, to understand inductor capacitor, we need more information on their time variance behavior. Okay, that is how the secrets will be coming slowly now. Okay, so now next question, everybody. For inductor circuit shown, fine. First bit, steady state currents, flux linkages in each inductor. Third, energy stored in each inductor. Okay, energy stored in each inductor. Fourth bit, verify law of conservation of energy. Fifth bit, verify law of conservation of flux. See, for the inductive circuit shown, please see the question, sir. For the inductive circuit shown, is pure inductors. Okay, for the inductive circuit shown, okay, first, steady state currents in each inductor. Okay, steady state currents in each inductor. Then flux linkages in each inductor, energy stored in each inductor, verify law of conservation of energy and law of conservation of flux. So this is now 18 amperes. Now this is now 1 Henry, 2 Henry, 3 Henry, 4 Henry. Okay, so the question is very simple here. Determine the steady state currents in each inductor, energy stored in each inductor, flux linkage in each inductor, law of conservation of energy and law of conservation of flux. Chalo, everyone do this. I'm giving you 1 minute time. Just write whatever answers you know. Just 1 minute, sir. I'm going to solve this. This is a very small problem. Okay, just do it. Okay, now see this, sir, everybody. See, I want the steady state current. See, like previous problem, if you take as an example there, here also in transient state, the moment I close the switch, then transients are valid now. Then all these flux linkages, induced EMFs will come and Faraday's law applicable, like which I told here. Okay, and now with that basics, I can easily do the current division. So that is why the previous problem, once you understand time variance, now current division. This is directly 18 amperes. Because for DC steady state also, all inductors act like short circuit. But before that steady state transient occurred, that time current division is valid. So I know all are short circuits. Then you may say, sir, all are short circuits and ideal wires. How can you divide the current? That means the same explanation what I gave here. So here also let us assume that 18 amperes is suddenly closed, transients will occur, and then they reach steady state, and that is how the inductors reaching steady state. Now current division rule. So now this total current is 18. Now current division rule. So this current will be, yes, this current will be total current 18 into, okay, 18 into opposite 6 by 9. So this is automatically how much now? Yes, this will be now 12 amperes. Then automatically this will be 6 amperes. Of course, series, this is also 6 amperes. So that is the first bit. First bit I got. Okay, now? Yes, now second bit, flux linkages. Now flux linkages in 1 Henry. Psi is Li. Li. L is 1, I is 18. So 18 volt second. 18 volt second. Okay. Then flux linkage in 2 Henry. Psi is Li. That is 12 volt second. Then flux linkage in 4 Henry. Psi is Li. 24 volt second. Then flux linkage in 3 Henry. Flux linkage in 3 Henry. I will write here. Okay. Flux linkage in 3 Henry. That is psi is Li. L is 3 into I 12. So 36 volt second. Now, why the units volt second came? See, why units volt second came? Why units for flux linkage is volt second? Volt second. See, actually, flux is flux into turns, Weber turns. That is also 1 unit. Weber turns is also unit. Okay, but that number of turns and flux are not that information not given. The constructional design details of inductor with how many turns and how many flux, that details are not there. So we cannot use this formula. But another formula is psi is Li. What is L? Inductance Henry. Inductance Henry, current amperes. But another unit for inductance is volt second by ampere. Volt second by ampere into ampere. So ampere gone. So unit is volt second. Unit is volt. Okay. Yes, volt seconds only, because V is LDI by dt, L is V into dt by di. So volt second by ampere into ampere is volt second. Okay, na? That is why the units of flux linkage is what? Volt second. Then energy stored, sir. Now this is direct, everybody. Chalo, energy stored. See it. Energy stored in 1 Henry. That is half L I square 18 square. That is how much? 162 joules. Energy stored in 2 Henry. That is half L. Where is 2? 2 is here now. 6. Okay, I is 6 square. That is 36 joules. Energy stored in 3 Henry. That is half L I square. I square. That is again 12 square. 12 square. Which is how much? 216 joules. Then energy stored in 4 Henry. That is half L I square. That is 6 square. That is 72 joules. 72 joules. Okay, na? So this is steady state. We got the energies. Now, law of conservation of energy. Yes, law of conservation of energy. Law of conservation of energy. Now, these are pure inductors. Sir. Pure inductors will never convert or dissipate. So, what we need to prove? The total energy delivered by the source, okay, is energy stored by the sinks. Total energy delivered by the source, okay, is energy stored by the sinks. Sinks are inductors. Sinks are inductors. Now, left hand side. Left hand side, total energy delivered by the source is half L total I total square. That is half into. What is L total? If you look at L total, now see, 2 plus 4, 6, 6 in parallel to 3, 2, 2 plus 1, 3. So this becomes 3. I total square, 18 square. Okay, I total square, 18 square. Okay, that if you do, yes, it is 486 joules. Then right hand side, energy stored. Energy stored. Okay, if you look at energy stored, that is 162. Okay, 36. Okay, 216. 72 joules. Okay, that will be again 486 joules. That will be again 486 joules. That will be again 486 joules. Okay. So here law of conservation of energy verified. Okay. But this is very interesting, sir. This EBIT, law of conservation of flux. Okay. Law of conservation of flux. So for that, yes, it is related to Faraday's law, that is induced EMF. It is related to Faraday's law. Okay, I will tell you why. Faraday's law, that is induced EMF. That is induced EMF. Okay, induced EMF means we have to consider the KVL paths. KVL paths. I will tell you the meaning. So what is that I have to prove? Now, flux is also electromagnetic property of matter. No one can create nor destroy flux, but it exists in electromagnetic material. So total flux linkages established by the source. Okay, total flux linkage established by the source is the flux linkages retained by the sinks. Retained by sinks. Of course, sinks are inductors. Okay, total flux linkages established by the source. Okay, is the flux linkages retained by the sinks. Okay, now total flux linkages established by the source is the flux linkages retained by the sinks. Okay, total flux linkages established by the source is the flux linkages retained by the sinks. Okay, yes, total flux linkages established by the source is the flux linkages retained by the sinks. Okay, so now in that regard, everybody, now in that regard, yes, what I'm trying to do is, yes, in that regard, now what I will do, now total flux linkages established, left hand side, total flux linkages established is L total into I total. What is L total, sir? We already know, yes, L total, 6 in parallel 3 plus 1, 2 plus, yeah, 6 in parallel 3, 2 plus 1, 3, nah. So this is 3 into I total is, however, 18. So total 54 volt second, 18 3s are 54 volt second, 54 volts. Now if you go to right hand side, yes. Now to find total flux linkages retained. Now you have to consider the KVL path. Now why? Listen carefully. See here also imagine that you are closing the switch at t equal to 0. Let us say there is a switch here and you are closing at t equal to 0. Now at that instant, yes, sudden change. Inductor will not allow sudden change in current, but if you do allow sudden change in short interval of time, impulse voltages will come. That means at t equal to 0 plus, what voltages are coming? Impulse voltages. Okay. Now that impulse voltages are due to impulse fluxes. Now according to Faraday's law, this change in flux linkage will induce EMF now. However, in steady state, inductors act like short circuit. Yes, however, in steady state, inductors act like short circuit. Please understand. However, in steady state, inductors act like short circuit. Yes, that is true. Okay. However, in steady state, inductors act like short circuit. But in transient state, when you suddenly close the switch, yes, at that instant, impulse voltages will be induced and Faraday's law is valid. Now to prove law of conservation of flux, which have divided during induced EMF concept. Yes, to prove law of conservation of flux, which have divided during induced EMF concept, consider the KVL paths. Now see here, sir, very carefully. There are two possible KVL paths. See from here to here. Okay, this is path 1. Okay, this is path 1. This pink color is path 1. Okay, I will write neatly. See from here to here. This is path 1. Okay, this pink color is path 1. Okay, pink color is path 1 for KVL. Path 1 or KVL path 1. Okay, now this is KVL path 1. Okay, then I can also take this blue color path 2. This blue color path 2. Yes, this blue color path 2 is also KVL path 2. So this is KVL path 2. So pink color and blue color, anything you can take. So now in this regard, if I take first pink color, okay, path 1. What are the inductors coming in path 1? Now what are the inductors coming in path 1? See 1 Henry and 3 Henry. 1 Henry and 3 Henry. That is flux linkage in 1 Henry plus flux linkage in 3 Henry. Now what is the flux linkage in 1 Henry? We already know, sir. See, flux linkage in 1 Henry is 18. Flux linkage in 3 Henry is 36. So that is 18 plus 36. That is total 54 volt second. 54 volt second. Then I'm going to path 2. Yes, then I'm going to path 2. If I go to path 2, Now, what are the inductors coming in path 2? See, in path 2, blue color line, 1 Henry, 2 Henry, 4 Henry are coming. Okay. Flux linkage of 1 Henry plus flux linkage of 2 Henry plus flux linkage of 4 Henry. That will be how much now? That will be 18 plus 2 Henry flux linkage is how much? 12 and 24. Okay, this is 12 plus 24 volt second. That is also 54 volt second. 54 volts. So see, sir, that is a verification of law of conservation of flux. That is a verification. Okay. So we'll stop today, sir. We will stop today. Tomorrow we'll go with much useful things. Now ask doubts, sir. Very cool. I will explain. Chalo, Vishnu, doubt?
Sir, my doubt is in this one problem where you started with the steady state currents in each inductor and energy stored in each. That switch is there in between.
Tell me. Tell me.
Sir, my doubt is in steady state we do consider that this inductor is being short circuited, right, sir?
Yes.
The thing is, at steady state, at this end of this problem, we did calculate the energy stored in the inductor. That is the steady state energy. That is the final steady state energy stored in the inductor.
Yes. Correct.
So my doubt is this energy will not oppose the flow of current.
No, the induced EMC after all these arguments will come when transient state occur, when there is a change in the system. See, this opposition will come when there is di by dt.
Okay, sir.
When there is a rate of change, then induced EMF will occur. But however, in steady state, there is no rate of change. Inductor will only retain that energy. This concept clarity you will get tomorrow in the second problem. Remember, see, tomorrow morning, when I do the second problem on time variance, when I give ramp current, there this concept I will explain. That what is the exact meaning of Lenz law and when you have to take half Li square and how can you take inductor current as state variable and energy stored in inductor at X is energy at X. Like that I will teach tomorrow.
Okay, sir.
Your argument, I understood that when this argument is valid, when actually there is a time variance. But here we are considering all those are over and it has reached a steady state. And in steady state, this current is constant, rate of change of current is 0. So when this have stored energy, it would have stored energy in the transient state when changes occurred.
Yes, sir.
Then it is retaining this energy in steady state. That is how this energy is stored up to infinity is energy at infinity for inductor.
Okay, sir.
That concept tomorrow, we will get excellent example tomorrow. Okay.
All right, sir. Thank you, sir.
Okay. Then Bimalendra Swine.
Yes, sir. Good morning, sir. Sir, that doubt is that in the last part that the Faraday induced law of KVL parts. Means if we are in individual KVL path, then it is valid. Then if we are sum it 54 plus 54, this is not valid.
See, that is what I'm trying to say. Individual KVL path only, because when the flux also would have divided, like I will give an example. Suppose you imagine that, like suppose in capacitors also the same concept will come. In inductors also similar concept. I will argue like this. That means in two series inductors, what is equal? Current is equal.
Yes.
But fluxes will divide.
Yes.
Okay, fluxes will divide. In parallel inductors, what is same?
Parallel that voltage is same.
No, you cannot say voltage here because it is DC steady state now, voltage is 0. So in parallel inductors, what is same? Flux linkages are equal.
Okay.
Currents will divide. So that means you cannot take 2 times.
Yes.
That is a concept. That means fluxes also will divide. Like charge divides in capacitor, current divides in resistor, fluxes also divide in inductor. So to prove law of conservation of flux, the induced EMF path has to be considered because that is the time when Faraday's law is applicable during time variance, the fluxes will divide.
Okay.
I will repeat this. See, that is the time when Faraday's law is applicable during time variance, the fluxes will divide. So to prove law of conservation of flux, I should now consider the induced EMF path. Induced EMF path means KVL only. Okay, that is the meaning.
Okay. Means here voltage, how is it not same? Means this is connected
because in DC steady state, of course, impulse voltages will come in transient state that we can plot also. But the real reason is in steady state inductor short, there is no voltage. But this time variance in transient state, the voltages came impulse, that time fluxes have divided. And then it is retaining. So to prove law of conservation of flux, I should consider the induced EMF path which is valid in the transient state.
Okay, means at steady state that voltage will be not same because there is some short circuit of that. Only flux can.
That is not there. No, that is not there.
Only flux will be considered.
Right, correct.
Okay. Thank you.
Right. Yogesh.
Hello. Yes, sir.
Tell me, Yogesh.
When resistor is there in series with the inductor, then how to apply current division, sir?
Then that current division is by resistor only. Like we did this problem. See, in this problem, Here no problem because they are like practical coils. Though inductors are short, now resistance is taking care about current division in steady state.
Okay.
If inductor alone come, then that concept of that is why pure inductor, pure capacitor to analyze these basics of time variance are important.
Sir, and if we consider in transient state at that time, sir?
Then no original problem with time constant, which is rising early, which is falling early, all this di by dt, di of 0 plus by dt, like that we will solve. That is more practical. That means before we go to practical, we are learning first ideal concepts.
Okay, sir.
Once we know this, then however in transient with practical resistor, time constants will come now. Tau equal to L by R, and that will decide if time constant is small, faster, higher rate, time constant is large, slower, late, like that we can talk.
Okay, sir.
Okay.
Thank you, sir.
Right.
Thank you, sir.
Yes. Shiva.
So good morning, sir. So law of conservation of flux.
Law of conservation of flux. Yeah, last problem.
Yes.
See, what I'm trying to say is here actually all are pure inductors without resistor.
Okay, sir.
Okay, if resistor was there, this confusion won't come. Like one student asked, then I would have gone to transient state, time constant, everything. But here, no. So first, pure inductors. Like I was giving this example, like you see, why can't we add all the flux linkage? See, generally students say, sir, all inductors are excited. Why can't we add all the total flux linkage and tell it is equal to source side? No. Why? Because here fluxes also will divide. Like charge divides in capacitor, currents divides in resistor, fluxes also will divide in inductor. But when this is valid to explain in transient state, suppose imagine that you are closing the switch here, this current source. We know inductor will not allow sudden change in current. But if you give sudden current, impulse voltages will come. That means these impulse voltages are valid in which point? Transient point, that t equal to 0 plus. Okay, these inductors voltages are valid in t equal to 0 plus, and that is the time Faraday's law, change in flux linkage will induce EMF. Okay, that is the time Faraday's law, change in flux linkage will induce EMF, and that EMF induced is valid in which state? Transient state. Now to prove law of conservation of flux, here we should consider the induced EMF path which has distributed the flux. The induced EMF path which has distributed the flux. Now listen. Now suppose there are two, you see this 3 Henry and this total 6 Henry are parallel.
Yes, sir.
Now here how to argue? See, we know in parallel inductors, currents will divide. But here voltage is equal, we cannot say because there is no voltage in steady state, short circuit.
Yes, sir. Okay.
So what we have to say is in parallel inductors, flux linkages are equal. So this total flux linkage is 12 plus 24, 36. This total flux linkage is also 36. So because fluxes are dividing, we cannot add all of them.
Okay, sir.
So we should consider the KVL path, which is actually dividing the fluxes in the transient state. So there are two possible KVL paths in this case. One is the pink path, one is the blue path. Any path you can take and prove law of conservation of flux. But of course, if all inductors are series, then you can directly add them.
Okay, sir.
Okay, like capacitors in parallel, charge you can add them. Inductors in series, fluxes you can add them. But inductors in parallel, fluxes are dividing. You cannot say no, sir, we will add separately. That is all happening in the transient state. And then that is the reason KVL path. This KVL path is valid when, yes, in transient state. That time this is fluxes are divided. That is why one path also 54 volts second, second path also 54 volts second, which is equal to the total flux linkage.
Okay, sir, but here, like the psi established means the 18 amps current source is established.
That is establishing. That is establishing.
From how come the same thing will retain the flux, sir, once it is established?
That is the meaning of law of conservation of flux. That you are proving that how much flux linkage established by the source is also flux linkages retained by the sinks, which are the inductors. That is why inductor, when you excite during time variance, they will store. If you maintain, they will retain. If you de-excite, they will give back.
Oh, okay.
Tomorrow the same problem I will take ramp current and explain. Then you see here transient 0 plus like sudden change is there. But if you take a ramp current, slowly it will rise, it will reach steady state, and again it will release back also if you de-excite them.
Okay, sir. So the 18 amps current source is establishing the flux when we are exciting them, and so it will retain and deliver the flux back when we de-excite them.
Yes, correct.
Yeah,
Yes.
okay, sir. Got it.
Yes, right. Okay, tomorrow 7 o'clock, everybody.